Now we will present application-free inhibitor performance in a coating defect. It will be done by Nourhan Abdelrahman from VUB. Nourhan, please start your presentation. Floor is yours.
Thank you for the introduction. I'm sharing my screen now. Hope you can see it.
Yes, all is okay. Please present.
Great. Okay. To start a bit about what App3 is, it's the motivation behind it is that this finite element simulation of the effect of active protective coatings. But what are active protective coatings? So it's a coating layer covering the surface of a metal. In our case, it's aluminum alloy 2024. This layer of coating provides protection for the metal surface from any corrosive effects of the environment as long as it's there. But then in the case of a scratch to this coating that exposes the surface of the metal, it also provides active protection through pigment particles in the coating layer that begin to dissolute and move towards the surface of the metal and provide a sort of protection by different mechanisms depending on the type of the particle. Now, this has been followed for so many years so far, and specifically in hexavalent chromium-rich compounds, and they have been working effectively. However, recently it has been found out that it has a health effect, so it's a carcinogenous nature is immense. And now there is a kind of road laid out to try to find alternatives for it. And the idea behind App3 is to try to use finite element modeling to help with this process of choice and new replacement for for chromate. Now, knowing that we have a certain geometry that we're looking at, so it's basically a metal layer half coated and half exposed to the environment. And the environment is basically a layer of electrolyte that has that is connected to the atmosphere. So we have also air dissolution in the electrolyte. And then we're trying to look at different domains of this geometry. So we want to try to study what's going on in the primer and in the primer interface with the electrolyte. So how is the pigment dissolving? In our case, particularly lithium carbonate pigment, and how it's diffusing towards the electrolyte. We also want to look at what's happening on the metal surface. So initially, when we have the defect, we will have the corrosive effect, so aluminum oxidation is occurring. And then later, as the lithium carbonate takes effect, how this protection effect is limiting the rate of corrosion. To do this, we need some helps from experimentalists. So some inputs are being used. For the part of the primer and it's interacting with the electrolyte, we're using some experiments from our partners AkzoNobel. So they're basically measuring how much lithium ion is found in the electrolyte over time. And then by retrofitting this, we can obtain the parameters of what's going on in the primer. And then the second input is from our other partners, TU Delft, and it's basically dynamic polarization measurements at different concentration of lithium carbonate. And this is to provide the effect of inhibition at different concentration of lithium ion. Now, to go into a bit of a depth of the experimental inputs that we have a software from our other partners, Elsica, that implements a percolation model equation that tries to fit the experimental data that we have to the parameters in the equation. And what it tries to take into consideration is how the formation of voids in the primer help with the faster dissolution of the pigments. I'm not going to go into details of these parameters, but all the parameters in blue are being fitted, while other parameters in black are initial conditions, and in orange are model, finite element model data points. The next part of the experimental data is the dynamic polarization. And in this case, we're trying to fit the parameters of a Butler-Volmer equation. We're also doing this in a 1D finite element model to obtain 4 parameters that change with the lithium carbonate concentration. Now, this is the background of what App3 has, but what a user can interact with is a kind of a varying the parameters of this background. So in case of inputs, a user can vary the geometry inputs like electrode thickness, topcoat thickness, primer thickness, defect depth, and defect width. It can also, a user can also vary the environmental conditions. So the salinity of the electrolyte or the initial inhibitor concentration in the primer. You can also try to change the solver input, so simulation time and measure solution. And then as output, you can monitor the change of different species that are listed here. We're trying to categorize them based on their relation. So electrolyte species, dissolved air, corrosion products, and inhibitor species. And you can usually see that in different forms. So it could be a GEF or domain average, domain maximum, and domain minimum. And now moving on to the platform. So starting from the landing page of my account, if I go here, I can go to degradation in defect App3. Now, the geometry is kind of described with color codes for demonstration, let's say. And then the inputs that we've talked about are listed here. So it should be noted that as you try to increase the geometry or as you try to increase the mesh resolution or the simulation time, the model will take longer to run. This is expected because, as we have been explaining so far, the complexity of the model is quite intense. So it's okay if you start running a model and you don't get the results right away. It can take up to even multiple days to give you the results. Now, let's try to set up a simulation in this case for 5 seconds. Now that I'm done building all my geometry, I can just set build geometry and set conditions, and I will see whatever I've set in the left side and the right side. And then below, I can just press run process, and it will tell me that my simulation has started successfully and that I will get a notification when it's finished. Now, the notifications will come in here, as Marco has described. A previous simulation run is here for me, for example. And once I get this notification, I can go to my user page, user data catalog, and I will find all my results here. Now, if we go to one App3 simulation, we will see the result that we mentioned in our presentation. So multiple GEF files that show the change in concentration of different species over time. And here the time steps changing. And if I go down, there is here the average concentration. So I can plot it for oxygen in the electrolyte, for example, and how it's changing over time. I can also save it as an image, but I guess this was covered by Marco already. As you see, this is an incredibly intense model. And that's why in our case, we have App5, which my colleague Lisa will describe, that gets us to the results that we want to see in a much faster path. However, App3 provides you the ability to try to study different conditions, let's say. So, for example, to try to compare the effective defect depth on lithium ion and aluminum hydroxide. You can see that as it's changing in 2D, or you can just see it as an averaged value over time. Different thing can be tested. You can test PVC, you can test electrolyte thickness. So in general, it's a way to try to test different scenarios. But for a more effective design, I think App5 will be a good example on how to do that. That's all for me, and thank you for listening.
Thank you very much, Nourhan.